Good morning. Welcome to the second day of NDC Porto. So how are we feeling today? How are we feeling after the party last night? Come on. I know it's 9 a.m. I want to hear a bit more from you. Yes. How has the conference been so far? Woo! Come on. I can't be the only one who's this energetic at 9 a.m. I have been up since 5 a.m. So if I can bring this, so can you. Okay, so I am honoured to open the conference today with a topic that is near and dear to my heart. And that is, can you trust your models? Now, of course, I'll be talking about machine learning models, but naturally, I have to focus quite a bit on large language models because it's 2024, and how else am I going to get a keynote? So, a talk like this requires quite a bit of research. And what you're going to see at the bottom of a lot of my slides are links to resources I've used throughout this talk. Now, if you want to follow up on anything, don't panic about taking photos. I am going to be sharing a QR code at the end of this talk, and it's going to take you to a link that contains all of my slides as well as all of those resources. But it does mean you're going to have to stick around until the end. I do promise it will be worth your time. So let's take a closer look at the title of this talk. Can you trust your models? Now, if any of you have ever worked with machine learning, you will know this is a difficult problem. It's a problem we have grappled with for quite some time. But it's particularly become a question in the last year or so with large language models, as we've moved from playground to production. And it's a difficult question to answer. But the thing is, this is not really a question about trust. This is actually a question about something far more tangible and far more scientific. It's a question about whether you are measuring the right thing. And in order to illustrate the difference between these two concepts, we're going to start with a story from real life. So back in 2010, a social psychologist called Amy Cuddy was teaching at Harvard Business School. And Cuddy began noticing differences between the behavior of some of her students. So some of her students, while they were doing very well in non-class participation, were absolutely failing at class participation. They didn't want to be there. They were shy. They would half raise their hands, almost as though they were trying to protect themselves. And correspondingly, when they did have to say something, they had no conviction in what they were saying. A second group of students, also doing well at the non-class participation, but they were killing it in class. They loved it. They wanted to be there. They raised their hands high, and when they spoke, they really believed in what they had to say. So, as is the case when you do psychology, you become a guinea pig for your professors. And Cuddy began to wonder whether this relationship between body language and confidence went both ways, whether potentially holding more confident poses could lead to people feeling more confident. And this kicked off Cuddy's research into what she called power posing. I'm seeing some flickers of recognition on some faces in the audience. So in Cuddy's experiments, what she got people to do was to hold a series of what she called high power poses, things like this one, the Wonder Woman pose. And what she found is that participants who held these poses reported feeling more powerful, yes, but they were more willing to engage in risk-seeking behavior, and most importantly, they showed physiological changes. They demonstrated, when measured, higher levels of testosterone and lower levels of cortisol, indicating that they actually felt more dominant and less stressed. So Cuddy's colleagues were impressed by these findings, as was the wider scientific community. And this earned her a publication in the top journal in psychology, Psychological Science. And then the findings hit the mainstream. Cuddy had press interviews. She got an appearance on Oprah, and she got one of the most watched TED Talks of all time. Remember TED? This was when it was really cool. So people everywhere were sneaking into bathroom stalls and power posing before job interviews, or holding these poses before doing something difficult, say walking on stage and doing a keynote speech. Cuddy and her power posing had become a mainstream phenomenon. That was until 2024. Another researcher, Ava Rainhill, tried to replicate Cuddy's findings, but she wasn't able to replicate most of what Cuddy found. And most importantly, she couldn't replicate those physiological changes, the jewel in the crown of Cuddy's original study. Other researchers took interest. They started looking into this themselves, and they built up a body of evidence that this relationship that Cuddy had found between confidence and body language didn't exist. This whole unhappy saga came to a point when one of the original co-authors on Cuddy's study publicly disavowed their findings, and Cuddy's credentials as a scientist were called into question. So what happened here? What happened to Amy Cuddy? How did she mess up so badly? Maybe Cuddy was a charlatan from the start. She was out to fool everyone and get a sweet speaking deal. Maybe she was incompetent. The thing is, neither of these things were true. Cuddy did her PhD at Princeton. She did this research, remember, while she was at Harvard. She was a rigorously trained scientist. The problem was that Cuddy and everyone else who had reviewed her findings was fooled by results that seemed true, but they told them the wrong thing because Cuddy had measured the wrong thing. So I know what a lot of you are thinking right now. It's psychology. Like, of course this was going to happen. But this couldn't happen to machine learning. It's so much more scientific. The math it uses is so complex. It is immune from such problems. Not so fast. So reviews have been done on a wide number of papers across a wide variety of disciplines that use machine learning techniques. And in every single one of the fields, at least 15% of the studies had serious problems with how they'd measured their results, which meant that those results were not true or correct. In some of the fields, you can see more than half of the studies had these problems. And I don't know what's going on in satellite imaging, but all of their papers had this problem. And you can see that this list includes arguably more objective or hard fields like genomics, medicine, and oh yes, software engineering. We did not escape. So let's have a look at an example of one of these studies. So what these researchers were trying to do was see whether 4 different machine learning algorithms would perform differently when given the same task and the same data. And what they found is that newer, more sophisticated algorithms outperformed boring old logistic regression, which is much simpler and much older. Makes sense, right? You know, you're going to have something more cutting edge. Of course, it's going to outperform something that's a lot older. Except none of it was true. They had made major errors with how they had actually calculated their results. And when these were corrected for, this result disappeared. Everyone was just as bad as logistic regression. So, it's a bit scary, right? If even experts in machine learning can make such grave mistakes, if mistakes like this can make it into the published scientific record, how can we be sure that our machine learning models are good? How can we be sure that we're measuring the right thing? So to answer this question, we can borrow from a field called measurement theory, which is, unsurprisingly, the branch of mathematics which tells us how to measure things. And measurement theory tells us that a robust machine learning model will have 2 properties. It will be reliable, and it will be valid. So reliability is basically saying that your model is consistent in its predictions. There's a few facets here. The first is that for equivalent inputs, your model will give you equivalent outputs. And this will also be stable and consistent over time. The model will give you the same outputs for the same inputs, whether it's 6 months later or at the time it was trained. And it also means that different equal ways of assessing the same thing will converge on the same answer. It could be that you have a machine learning model that's doing predictions and human raters. They should converge on the same predictions. Validity, on the other hand, is measuring what you set out to measure. And this seems super easy, right? Like, how can you not measure what you set out to measure? But we're going to see this is a very slippery concept, and it's very difficult to actually get it right. So validity involves having a well-defined and precise concept that you're trying to measure. It also means that you have a sanity check. If you have something that you trust that's measuring something similar, again, those results should align, they should correlate. And it also means that your model should perform just as well out in the real world as it does in its nice protected little development environment. So let's first have a look at a major threat to reliability, and that's the problem of data leakage. So for me, I think the easiest way to understand data leakage is to understand the problem that a professor giving an exam faces. So imagine you are this professor. You want to assess your students at the end of the semester, so you give them an exam. To help them practice, you give them past exams. But when it comes time to preparing the final exam, you have fresh questions, ones they haven't seen before. So this way you are sure that what you're measuring is how well they've learned the course content. Let's say you're a little lazy maybe, running a little low on time, so you have to reuse past exam questions. Now this creates a measurement problem. You are no longer sure what you're measuring, and it's quite possible what you're now measuring is how well the students have memorized the answers on those past exam questions. So this is the problem of data leakage. You give the students the materials to, you test the students on the same material that you use to train them. So this works in the same way in machine learning models. We can see that in the case of a model called ChexNet. Now, ChexNet was designed to automatically test whether someone had pneumonia based on their lung scans. And when it was first released, it worked super well. Hooray for science, right? We've solved this problem. Except we did not. There was a problem with the data. And that was that when people go in to get lung scans, they don't just get one lung scan in the same appointment. They get multiple. They're basically identical. And the creators of this model did not know that. So what they ended up doing is distributing identical lung scans across the data set used for training and the one used for testing. When it came to test time, well, the model had already memorized some of the answers. Do you see the problem? It is just like with the students. So let's now turn to validity. So in the early days of machine learning models, when we had models like regression models or decision trees, assessing validity just by looking at what a model had learned was really easy because these models are completely explainable. You can see exactly what they've learned during training. So we can see an example of this with a linear regression model. So this model here is assessing or predicting students' exam scores. And we can see that we've got a number of features, the things that we want to predict the exam scores with, and each of those features have weights. These weights tell us exactly what the model has learned about each of those features during training. So example, this 1.5 next to hours spent studying tells us that what the model learned is that for every hour the students spend studying, they will get an extra 1.5% on their exam mark. Super interpretable, super easy to understand. But as we've moved into more complex models, the age of black box models, things have become a lot more complex. We've had to create layers of interpretations or workarounds to try and work out what models are learning during training. So for example, with this vision model, we can pull out the hidden states and we can try and sort of visualize what the model is learning. Looks like this model is sequentially learning what a cat looks like, but I've had to interpret that. I could be wrong. Or this early small language model, we can see how it seems to be learning the relationships between words in a sentence. But again, that's not really the full picture, and I don't know if I've interpreted this correctly. And things have really gone off the rails with validity when it comes to large language models. We can peek inside these models to an extent, but it's in a very, very limited way, and in no way encapsulates the full kind of capabilities of these models. So what we're stuck relying on at the moment is looking at the model inputs and seeing whether the model outputs make sense. So say we have this example here. Write me a joke about cats. Well, it did give me a joke about cats, but I don't know how it arrived at the concept of a joke or how it knows what a cat is. And what's worse is we don't just have problems with validity, we have serious problems with reliability. This is a problem we never had before with machine learning models. Once you had trained a model, it would give you the same output for the same input. But anyone who's used an LLM will note that by design, they do not work that way. Same input, two different cat jokes. At least you could say they're equally terrible, but that's not really a reliability measure. So this brings us back to our question. How do we know if a large language model is good? How can we measure these models correctly? Well, if you've been a person existing in the world for the past year or so, you will have LLM vendors and developers telling you how very good their models are. So perhaps you will have read a piece of marketing material from an LLM vendor that says something like the following. We've just launched our newest large language model, trained with state-of-the-art GPUs, and we've improved on the MMLU by n points, beating the previous best. Or maybe you've seen some flavor of an LLM leaderboard pitting models against each other on exotic-sounding measures like Winogrand or Hella Swag. Hella Swag! It's one of my favorite named things in machine learning. But the thing is, what are these things measuring? And does scoring really well on these benchmarks mean that an LLM is good? Welcome to the noisy and confusing world of LLM assessment. So let's start with what I think is one of the most inflammatory ways of assessing LLMs. That's seeing how they perform on benchmarks that were originally designed for humans. So we can see an example of that here. What we have are 4 language models, and they've been given questions from a US medical exam. They did great. GPT-4 got 100% of the questions right. Worst performing models still got 75% right. Probably better than I could do. Most definitely better than I could do. So results like this were everywhere early last year. We had people applying LLMs to medical exams, to law exams, to lead code puzzles. And then the corresponding claims followed. If they're so good at smashing these super difficult exams, it won't be long until they replace doctors, till they replace lawyers, till they replace programmers. The thing is, it's been over a year since we saw these results come out, and we haven't really seen that much progress towards these goals. Really, I would say no material progress, but you can come and argue that with me afterwards if you would like. So what gives? Why have we not been able to translate this amazing exam performance into replacing doctors? So if you've been to any of my previous talks, you'll probably know what I'm going to say next. And that is the problem with taking assessments that were designed by humans and applying them to LLMs is that you're fundamentally measuring different things. Now let's talk about why we give exams to humans. What do they measure? And let's take the case of medical exams. The point of giving medical exams to students is to act as a proxy, a predictor of how well they'll go when they have to practice medicine. And they're not perfect, I don't want to kind of defend them, but studies have been found that they do have validity. The people who go on to do well at these entry exams for medical school go on to do well at med school and then go on to have quite successful careers in medicine. So the reason that we can make this connection is because the mechanism for being able to complete difficult medical exams and to be able to practice as a doctor both tap into the same raw general ability we have as humans called G, or general intelligence. So humans can use G to solve a whole range of problems. We are generalists, we are very flexible. And in the case of exams, we can use things like advanced reasoning and learned knowledge to solve medical exams and solve medical problems alike. So what does it mean when a large language model does well on a medical exam or a law exam or something else? It means that they're good at solving the specific kinds of problems that are present on those exams. Nothing more, nothing less. But why? Why is it that we can't make this leap? We can't say that this exam performance is a proxy for a higher intelligence in these models. So if you're really interested in this topic, I've talked about it extensively in other talks. I gave a talk at NDC Oslo where I have a whole section on intelligence in LLMs, but we'll just keep it brief for this talk because we've got a lot of other things to talk about. But in brief, the problem comes down to how LLMs learn compared to how humans learn. So humans, as I said, we have this general ability to learn. We can solve many and diverse problems using our general intelligence. Machine learning models, on the other hand, are trained to do one thing and one thing only. In the case of ChexNet, this is to detect whether people have pneumonia. And in the case of LLMs, this is to predict the next word in a sentence. So for each batch of training data, what an LLM needs to do is generate some sort of prediction. They then need to compare that prediction against the correct answer, a gold standard. They need to see how far away they are from that answer. Then they need to gradually adjust the model weights and then continue the whole thing again until they hopefully get to some sort of good performance or convergence. Now, this is cumbersome. And in order to make this process as efficient as possible, neural nets have been designed with mechanisms in mind, like gradient descent, that helps them take the quickest path possible to that training goal. Because of these efficiencies that have been built in, because of all the other things the model needs to learn from scratch from the data, it's very unlikely that that path will include a detour into generalized intelligence. So, benchmarks for humans are no good. So let's go back to benchmarks that were designed specifically for LLMs. So up until recently, this very humble-looking table is one of the key ways that people worked out whether LLMs were good. So this is created by a company called Hugging Face. And what it did was it would take open source LLMs, get them to complete a bunch of gold standard benchmarks, collate the scores, and then rank them. But in June of this year, something rather strange happened. This leaderboard was retired, and a new one using new gold standard benchmarks was introduced. What went on here? Well, part of the problem, there were a few, but this is the most entertaining one. Part of the problem was that these gold standard benchmarks were not quite the gold standard that people had held them up as. So we're going to go through a few, and let's start with the case of the MMLU. We met the MMLU a few slides ago, and this measure is so important in the assessment of LLMs. Major LLM vendors will compare their MMLU scores to a couple of decimal places. That is how highly regarded this measure is. But the MMLU also contains questions like the one I'm about to show you. And before I show it to you, I need to stress, I have not left anything out. I've not taken this out of context. This is the full question. The complexity of the theory. All right. Maybe there's a bit of a clue in the answers. So let's have a look. 1, 2, 3, 4. 1, 3, 4. 1, 2, 3. 1, 2, 4. There's nothing deeper here. This is the full question. This is all the information that the LLM has to work with. And this poor model has to try and predict that somehow C is the correct answer here. Okay, let's have a look at another one. This is from HelloSwag. This was also a leaderboard measure. And what an LLM is expected to do with HelloSwag is complete scenarios that it's presented with. Again, I have typed this out exactly as it's in the benchmark. The typos are not mine. Men are standing around in a large green field playing lacrosse. People is around the field watching the game. Men are holding t-shirts, watching into lacrosse playing. Are being interviewed in a podium in front of a large group and a gymnast is holding a microphone for the announcers. Are running side to side of the field, playing lacrosse, trying to score. Are in a field, running around, playing lacrosse. Now, whenever I read this question, I feel like I'm having a fever dream. But typos and bizarre imagery aside, we're meant to pick that the men are playing lacrosse, right? There are two options, C and D. What's the LLM supposed to do here? All right, one more, and I promised I could actually go for the rest of the talk with these, but we have other things to talk about. So this is from Common Sense QA. This is another popular measure. And we're off to a good start. This question actually makes sense. When a person is breathing in a paper bag, what are they trying to do? But hold on to your hats, let's see the answers. Warm air, continue to live, going to sleep, hyperventilation, stay alive. So I would say there's not even grammatical sense here, let alone a correct answer. And it does feel a little like I've cherry-picked these, right? Like maybe I've just gone through and these measures are totally fine, there's just a couple of bad answers. But no, there are dozens, maybe hundreds of questions like this, peppered throughout popular benchmarks. So in light of this problem, the creators of the Hugging Face leaderboard sourced more accurate, better curated measures. And they have retired the old ones and brought in these new ones. But what does this mean? Does it mean that if an LLM gets 100% on all of these new benchmarks, then they're a good model? Well, of course you know at this point of the talk that I am going to tell you no. Sorry, I'm really not. I was a clinical psychologist and I study stuff like depression. I'm not a very cheery person. Anyway, so one of the problems comes down to something very fundamental, and that is how LLMs actually answer the questions themselves. Doesn't matter what the questions are, the answer type has an influence. So LLMs, just like humans, have two ways in which they can answer these benchmark questions. So the first is multiple choice, just like we have in our exams. So say we present an LLM with the question, what is the capital of Portugal? We can present it with a few different multiple choice options. And if it picks B or Lisbon or some combination thereof, we know that this is the correct answer. Or it can, of course, generate free-form answers. So for our question about the capital of Portugal, if it tells us something like the capital of Portugal is Lisbon, this would be correct. So as you might have seen so far, all of the benchmarks that I've shown you so far use multiple choice. And the reason for this, as you can imagine, it's actually really difficult to see whether a fully free-form generated answer is correct, whether it is semantically equivalent to the gold standard that's put in the benchmark. So what's the problem then? Why don't we just use multiple choice for everything? Well, as I have hinted at, the answer type drastically influences the performance that LLMs have on these benchmarks. So here are three models, and here is their performance when they were given multiple choice options. Here are the same models for the same benchmark when they were asked to generate answers. So you can see in every case, it's worse, sometimes significantly worse, and that's bad enough. But what makes this really bad is they don't get the same questions correct between the two answer types. What this means, it's a validity issue. These two answer types are themselves measuring different things. And what researchers believe is that, unfortunately, multiple choice taps more into rote memorization, whereas generating free-form answers requires potentially more creativity and logic from the models. Another validity issue is that these benchmarks don't really seem to relate to performance in other measures measuring something similar. So let's take the case of this simple logic puzzle. Alice has 3 brothers, and she also has 6 sisters. How many sisters does Alice's brother have? Give you a couple of seconds. Has anyone got the answer? 7? Good. So let's see how we will solve this. So Alice, we must assume, is a woman's name in this puzzle. So Alice is one of the potential sisters. We're also told that there are 6 additional sisters. So if we add 1 plus 6 we get a total of 7 potential sisters for each brother. I see the frustration on some of your faces. I think next time I give this talk, I'll give you a bit more time. Sorry, I didn't want to take away the chance to solve a puzzle. The link will be, and you can solve all the puzzles yourself. So this is part of a suite of puzzles called Alice in Wonderland. And they're all quite similar, and they're of a similar level of complexity. So these would fall into, they're still simple reasoning puzzles. They're nothing too advanced or multi-step. So what the developers of these puzzles did is they got state-of-the-art LLMs. I'm talking like ones that are state-of-the-art now, to complete all of these puzzles. And then they also got these same models to complete the MMLU, our old friend. And the MMLU is also supposed to assess reasoning. So what you would expect in this case is that their scores will be highly correlated. If you get more MMLU items correct, you get more Alice in Wonderland puzzles correct. But what they found instead was a pattern like this. What does this mean? Well, what it means is that every single one of the models got significantly more MMLU items correct than Alice in Wonderland puzzles. And worse still, most of these cutting-edge models couldn't even complete 5% of the Alice in Wonderland puzzles, but could complete more than 50% of the MMLU items. So this tells us two things. It tells us that the MMLU is probably not really assessing reasoning in the way that we think it is. And it also means that a lot of these cutting-edge models have far weaker reasoning ability than we have been sold. And this leads to a question. These are language models. It's in the name. So should we even be trying to assess things like reasoning when we look at these models? Sorry, just checking the time. Good. So let's think back to the beginning of this talk, where I talked about the domain for creating and assessing machine learning models. So the way we've always traditionally thought about this in machine learning models is in a very focused way. Say like this vision model. All it does is tells whether an image is a cat or a dog. And so you will train it that way and you will assess it that way. In the beginning, it was the same with large language models. They were originally designed actually for machine translation. And so you would assess them based on whether they could do that task well. And so the original suite of benchmarks for LLMs were NLP benchmarks, natural language processing, seeing whether these models could successfully do tasks like question answering, whether they could do text classification or text summarization. And they weren't perfect. We've seen that already with the answer type issues, but they were at least focused on one specific task. But as the capabilities of LLMs have grown, or they appear to have grown, we have scrambled to create more and more exotic benchmarks. We now have benchmarks to assess advanced reasoning, to see whether these models can do a whole range of tasks or know deep knowledge in topics that are, extremely difficult, like physics or mathematics. And we even have benchmarks to assess whether these models have artificial general intelligence. Now, this for me is one of the core problems with using benchmarks. We create these leaderboards. We collate scores for all these different benchmarks assessing different things. But how do you then pick a model based on your problem domain? Are you trying to create AGI? Do you care about advanced reasoning? No, you're probably just trying to build a chatbot. So this is again a validity issue. By trying to create benchmarks and summarize them to assess LLM performance, the benchmarks have lost precision. They have lost meaning for the domains they actually matter to. So, those of you in the know might be screaming internally right now, what about the Chatbot Arena? And those of you who have no idea what I'm talking about, you're probably thinking, God, hella swag, Chatbot Arena, like what's wrong with these machine learning people? We do love weird names. So, the Chatbot Arena is an experiment. Anyone can visit the website where it's set up, and what you can do is enter a prompt, anything of your choice. So in my case, I have asked, can you please write me a poem about sausages? So then the Chatbot Arena will go away and it will find 2 state-of-the-art LLMs and ask them to return you an output. And you're asked to choose which one you like best. Quite fond of the second one. Plump and juicy, in a row they lie, sausages waiting to satisfy. So my experiment, and everyone else who visits the Chatbot Arena, they will be collated in a new score called the ELO score. This gives us another way of ranking and comparing models. And then, of course, they have built a leaderboard on top of this. So the Chatbot Arena and its associated leaderboard are considered the most trustworthy way of picking LLMs at the moment. It bypasses all of those pesky problems that we just talked about with benchmarks. And in a sense, it's true. So the Chatbot Arena is currently based on more than 1 million experiments coming from a diverse range of users, all with diverse preferences, and all coming in with their own unique prompts. So yes, in this sense, the Chatbot Arena has high validity because it is exactly how the end users of LLMs will receive the content. But before we get super excited and jump up and down cheering and assuming that we have solved this problem of LLM assessment, let's first look at how the Chatbot Arena actually assesses the results of each experiment. The words that you are required to use to choose between the 2 outputs are good and bad. But what does good mean? Does it mean more formal, more beautiful, more concise, more verbose, more funny? And does my sausage poem being good mean the same thing as a resignation email to your boss being good? Again, we come back to the problem of precision, just like with the benchmarks. By trying to create models whose use case is anything you can think of at this point, the only way we can possibly assess them is with terms that are so vague, they essentially become meaningless. So you might have noticed that I have been speaking extensively about validity, but I haven't really touched yet on reliability. So let's now go back to our old friend, data leakage. Now, LLMs are trained on absolutely enormous public data sets. We're going to talk about how big in a second. And in addition, the creators of these models have become more and more secretive over time about what data they're actually using. Even open source model creators are pretty cagey about their secret source at this point. So what this means is us as end users can easily be fooled into thinking we're seeing impressive capabilities of these models when we're just seeing memorization, we're just seeing data leakage. And there's a really beautiful experiment that a guy called Horace Hay did at the beginning of last year. He was very cynical about these claims that LLMs completing leak code tests meant that they had reasoning capabilities that exceeded developers, and he suspected data leakage. So what he did is he took puzzles from a website called Codeforces, which also has coding puzzles. And what makes Codeforces amazing for this little experiment is the date that each puzzle is released is clearly stamped. So Hay took 10 puzzles from the time that GPT-4 was trained. So it should have had access to these puzzles during its training period. And when he passed them through the model, it got all of them correct. Then what he did is he got another 10 puzzles of an equivalent level of difficulty, but these were only released after the model had finished training. And this time, it got every single one of them wrong. This feels like a data leakage issue, right? And another researcher, Saj Kapoor, confirmed this by explicitly asking the model about a Codeforces puzzle that it should have had access to during training, and it confirmed that indeed it did. So this data leakage problem causes so much confusion when it comes to the assessment of LLMs. And the rot goes deep. It even affects benchmarks. So a review of more than 100 benchmarks that were used to assess a variety of LLMs was done. And at least 100 of them were found to at least partially leaked into ChatGPT models. You can see that 75 question answering benchmarks alone had leaked. And all of the major ways that we use to assess these models, things like natural language capabilities, things like programming, and things like math, were affected. So this leakage problem is compounded by the fact that the amount of data that we have that's of sufficient quality to train and assess these models is actually a limited resource. It's finite. And we're close to running out of it. So the current wisdom is about how to make more and more performant models, more powerful models, are the so-called scaling laws. And this is the idea that you just make a bigger model and you feed in more data. And we can see the trend, right? We go from GPT-3 in 2020, which was trained with 500 billion tokens, up to Llama 3 this year, which was trained with 15 trillion parameters. That is a 30-fold growth in the amount of data used in just 4 years. The issue is that the amount of data that's available for training these models is estimated to top out at around 300 trillion tokens. And if we keep training models at the current rate, we're going to run out in potentially a little bit less than a decade, maybe in the next 3 years. Now, this is data leakage at a level we have never seen it before in machine learning. And with so much of the public internet consumed by these models in their voracious need for more and more data, how can we find clean pieces of data to assess them properly? The creators of benchmarks have made moves to keep the current generation of benchmarks private, so they will never make it, in theory, into the training data. But for us as lay users, how can we tell apart seemingly impressive performance on these models from something it's simply memorized? So to end this section on reliability, I want to talk about everyone's favorite topic, and that is prompt engineering. But sadly, I'm not going to be able to tell you how to get $1 million job in Silicon Valley. I'm going to talk about something a bit more depressing, and that is prompt sensitivity. So we want to classify a piece of text. We have a passage of text. So we can create a little prompt template for our LLM to do this by passing in the passage and then the list of possible categories. So, nice little template. Maybe we use this. Or maybe we use any one of these prompt templates. Can anyone spot the difference between these? Shout it out. Yep. Punctuation, spacing, capitalization. You are such great developers. Very well spotted. So these are trivial differences, right? This is natural language, right? Not programming. So we should not expect that these templates have any influence on the performance of our LLM. Well, let's see. So what this line here represents is the performance of the LLM on the task. So 0 means it got nothing right, and 1 means it got everything right. And these tiny, insignificant differences between the prompt templates led to a 77% difference between the best and worst performing prompt. Jesus, indeed. Now, this result is extraordinary. If we think back to traditional machine learning, if I built a model at work that was so unreliable for basically equivalent inputs, I get fired. That model would not be usable. But this is unfortunately part of the fabric of LLMs. To hammer this point home, this is not an isolated incident. In a review of models that were probably cutting edge about 6 months ago, you can see a similar pattern, between 30 to 50% difference between the best and worst performing prompts. Now, what makes this more troubling is that there is no universal prompt template. We can't just use one prompt template and get excellent performance out of every single model. There is a unique fit between each model and the type of prompts that it likes. And what this means is that us as end users probably don't know these ideal prompts. And so we're likely getting anything from a little bit worse to maybe significantly worse performance on these models than advertised. So, as is kind of typical at the end of my talks, you may be feeling a little bit depressed now and thinking, what's the point? Why would I use LLMs? Can't even tell if these models are good. Well, I have a potential solution for you. There is a silver lining, but it's not as sexy as leaderboards, and it's not as easy as out-of-the-box benchmarks. It instead is very similar to the way that we've been measuring and monitoring software applications for decades now. And in order to illustrate this, I want to go through a blog post that I read from an engineer called Hassan Hussein. And he talks about his experience with his team building an AI assistant for real estate agents. This is a magnificent blog post. Again, it'll be available in the list of resources. Can't quite cover everything in the last 5 or 10 minutes that I have, but I highly recommend you go away and read about this if you're interested in the topic. So Hassan describes how he and his team started the way you would kind of think you should. They picked a good model based on leaderboard performance, and they covered all the basic use cases for the real estate agent based on prompt engineering. Worked really well for a little while, and then it started showing problems. As more and more edge cases came in, they scrambled to try and cover them by creating more and more complex prompts. And then they had no real way of assessing whether it was better, so they were doing vibe checks, like hey, maybe it feels a bit better. It was a mess. So they decided to go back to the drawing board and take up a more systematic approach to assessment. So the first thing they introduced were unit tests. And the second thing they started doing was logging traces. Well. This feels a lot more like a familiar software engineering problem and less like this esoteric, hella swag machine learning magic. Then they introduced higher level evaluations, manual evaluations and A/B tests. And then they used the findings to incrementally improve their models and built this into a virtuous cycle where they could rapidly iterate and make small but meaningful changes to their model. So let's go through the 3 levels of assessment that Hassan describes in his blog post. And of course, the first is unit tests. So unit tests in Hassan's kind of estimation in LLM systems work much the same way as they do in traditional software applications. So LLMs, like many applications, have many user workflows. And what you want to be able to do is assess whether they're working correctly. So for example, in this real estate assistant, you might have someone asking for a phone number. So the workflow that that's going to trigger is that query or that prompt from the user to the LLM will prompt the LLM to create a query to the CRM and return the phone number. So the answer you want to, or the thing you want to know about this workflow to know it's working correctly is that just the phone number is returned. So for example, you could do a unit test just checking that an array of 1 is returned. You get a bit more fine-grained, but you get the picture. This is very familiar territory. Another thing that Hussein points out you can do is you can use a different LLM, the one you're not using to build your system, and get it to generate test cases. So let's say the workflow that we're trying to assess is retrieving contact information. So we can get it to come up with a bunch of fake contacts and fake user prompts. And then from that, build a variety of tests. So something I really need to emphasize here is I'm not advocating to automate the whole thing using LLMs. You still need to write and validate those tests the old-fashioned way, although of course you can use coding assistants to do so. It's more the idea that you're trying to assess a concrete output of an action produced by your LLM, and you're also getting a little bit of a helping hand from the LLM to generate more test cases. And now, of course, an approach like this has high validity. We have well-defined and precise concepts. And by using the LLM to generate more test cases, we make that more robust. We potentially capture all the different ways that users are thinking about that particular concept. Now, the next thing that Hussein advocates for is getting humans in the loop. And basically what this involves is going to your traces. So the traces in the context of an LLM application are those complex multi-step interactions that LLMs have with both the end users and other parts of the system. So you're probably thinking, oh my God, this sounds like a lot of work. It is, but you don't need to evaluate every trace. You need a representative sample of how your users are interacting with your system, and you also need to just get enough of them to get a feel for whether those workflows are working correctly. The good news is once you have enough of this data, you can start automating it to an extent. So you can introduce, again, a different LLM, and you can get it to start doing the same evaluations. And then what you want to make sure is that the assessments that your people have been doing and your LLM does converge. Obviously, the gold standard is the manual evaluation, and that is you end up with high reliability between your manual and your automated assessments. And then, of course, we have A/B testing. So once you're ready to go out and show your beautiful application to your customers, you can start playing around with a bunch of different conditions. Maybe you want to try a different LLM from the one that you originally implemented. Maybe you want to mess around with different prompts. And maybe you even want to try building a fine-tuned model based on the data that you've collected so far. Now, obviously, A/B testing, just like the Chatbot Arena, has high validity. You're testing exactly how your system works with end users. Possibly also, it's just a hypothesis I have, because you are able to mess around with the prompt LLM fit that is specific to your users and your LLM, you might be able to get more reliable outputs from the model. So hopefully, maybe I've inspired some of you to become LLM QAs. This, I think, is a viable career for the future. So we come to the end of the talk, and what we've seen on this journey is the introduction of LLMs has turned traditional machine learning assessment on its head. And attempts to take shortcuts in assessing these complex models has really confused us and widened the gap between assessment and reality. Along the way, in all this confusion, we've not really understood the true capabilities of these models. And in fact, we started creating myths about potential superhuman capabilities that these models have. Again, if you want to hear someone dispel that, that's me. That was my NDC Oslo talk. So, in reality, these models are powerful. They have very concrete use cases. They are powerful language models. And if you want to exploit these powerful capabilities, there are no shortcuts when it comes to assessment. It's just like it's always been. You need to create concrete and well-defined use cases, and you need to create and craft and monitor your own bespoke, reliable, and valid assessments. Whoa, wrong way. I was so smooth up until then. So here we are at the end. Here is the QR code. Here are my socials. And thank you very much. I'll be around for the rest of the conference if you want to catch up and ask any questions. Thank you. You liked it?